You're on candid camera or whatever it is. All right, so let's go ahead and start. Read along with me. If you did need your computer open because you can't see that because it's like way over here and there's stuff blocking the screen, feel free. What you'll learn what radioactive decay is, what half-life means, how radioactive isotopes are used. Yesterday we got started modifying our periodic table. Feel free to do that today as you need to. I will probably maybe have a bad drawing of an alpha particle that we put in there off of the reading. So anyway, it says before you read, every person's different. What are some things that make one person look different than another person? Go. Tone? Or how toned they are? Like a little more muscular than others, some folks? Yeah. Okay, all right. What else? They're the genes they're wearing? Genetics, right? Okay. Freckles. Some people have freckles. Some people have long, straight hair. Some people have short, wavy hair. I'm just looking around the classroom. Yeah. Well, if you don't consider that to be a construct, I'm not one of those, but it means something that was just made up by people. Okay. All right, moving on. Read to learn. Identifying numbers. The electron cloud model is an example of what? Hey, Kip. Parvis. What are we doing right now? Huh? Just read along. Okay, read along with me. The one worry I have when I do readings for folks is I'm like taking that away from them. It doesn't have to be that way. If you read along with me silently as I read aloud, you'll still get the benefit of reading. Does that make sense? Yes. All right, so the electron cloud model is an example of what an average nuclear atom looks like. We saw that yesterday, so if you weren't here yesterday, you'll see that when you make up the work. But what makes atoms of different elements different? The atoms of different elements have different numbers of protons. The atomic number of an element is the number of protons in the nucleus of an atom of that element. The element hydrogen has the smallest atomic number. It has only one proton in its nucleus. So hydrogen's atomic number is 1. That's what gives it its identity. We talked about that yesterday, right? I think we put that in our notes. The element uranium has the greatest atomic number of a naturally occurring element. It has 92 protons in its nucleus. Its atomic number is 92. There are synthetically made elements, man-made elements that go bigger than that. How many neutrons are in the nucleus? A certain type of atom can have different numbers of neutrons in its nucleus. For example, most carbon atoms have 6 protons and 6 neutrons. The vast majority, right? We saw that yesterday with the atomic mass being 12.011. But some have 7 or 8 neutrons. All of these atoms are carbon atoms because they have 6 protons, and that's what gives it the identity. These carbon atoms with different numbers of neutrons are called isotopes. Remember in our definition we said versions, different versions or isotopes of. Are atoms of the same element with different numbers of neutrons. Carbon 12, 6 and 6. Carbon 13, 6 and 7. Carbon 14, 6 and 8. Together, the protons and neutrons make up most of the mass of an atom. Electrons have mass, but it's really small. Okay? What is the mass number? The atomic mass or mass number of an isotope is the number of neutrons plus the number of protons. The table below shows the mass number and particles for the isotopes of carbon. For example, carbon 12 has 6 protons and 6 neutrons. If I scroll down, you'll see all that. Okay, actually, we'll just not read that. We'll just look at the table. So here's carbon 12, mass number 12, 6 protons, 6 neutrons, 6 electrons, atomic number 6. And then you can see the difference for yourself here. Carbon 14 is special because why? Do you remember me saying it was radioactive? What is the strong nuclear force? Ooh, back up. Number 1, evaluate. How many more neutrons does carbon 14 have than carbon 12? Huh? 2. Good, 2 more. What's strong nuclear force? How do you hold things together? You might use tape or glue. What holds the protons and neutrons together in the nucleus of an atom, though? Remember that protons have a positive charge. You might think that the protons would repel each other, but when the protons and neutrons in a nucleus are tightly packed together, an even stronger force, like a short-range force, takes over, a binding force. This force is called the strong nuclear force. The strong nuclear force keeps the protons from repelling each other. This force works only in the nucleus of an atom. Just try to focus. We're up here reading. Do you understand? Okay. Positive radioactive decay. The nuclei of most elements, are stable because they have the same number of protons and neutrons. For example, carbon-12 is stable because its atoms have 6 and 6. Some nuclei are unstable because they have too many or too few neutrons. So the particles in the nucleus try to repel each other. There's not a balance. The nucleus must eject or release a particle to become more stable. When a nucleus lets a particle go, it gives off energy. Radioactive decay is the release of particles and energy from the nucleus. Number 2 on the side, what keeps the protons in an atom from repelling each other? Right here, strong nuclear force. If you need to put that in your notes, the strong nuclear force is what keeps the protons in the nucleus from repelling each other. Yes? Sure. And that force we only see that in the nucleus of an atom. It's a very short range attractive force. All right, moving on. Transmutation. When protons are released from the nucleus, the atomic number of the atom changes. So one element can actually change into a different element. Transmutation is the changing of one element into another through radioactive decay. Now, there's a couple of types of decay that we're going to talk about. Okay? Alpha particles are lost. I think yesterday we mentioned alpha particles in the reading, right? So we're going to learn a little bit more about that. Smoke detectors contain the element americium. Americium? There we go. Maybe somebody pronounces it americium. I don't know. You good, Hall? You paying attention at all? Even a little bit? All right, I appreciate it. This element is unstable and undergoes radioactive decay. Americium-241 transmutates into another element by ejecting an alpha particle and energy. An alpha particle is a particle that's made up of 2 protons and 2 neutrons. The energy and alpha particle that are ejected are called nuclear radiation. In a smoke detector, the alpha particles make it possible for the air to conduct an electric current. As long as the electric current flows, the detector is silent. Smoke will interrupt the flow of the electric current and the alarm will go off. Okay, alpha particle. Put this on the back of your periodic table, or not, you know what, put it on the front of the periodic table. So you have all of the elements in the periodic table. You got a little bit of room on the bottom side somewhere. Yes? Well, I gave it to you last week, but do you have this one? The printed off periodic table? If not, it's fine. I got more. If you can't find it, here's one. So draw as best you can an awesome diagram like I'm about to. So we're going to just draw a couple plus signs and then leave the other ones alone. 2 of each, protons and neutrons. This would be an alpha particle. Okay. 4 little circles stuck together. 2 of them would have a plus sign because they're protons. The other 2 would have nothing in them because they're neutrons, no electric charge. Together they form what's known as an alpha particle. Okay, continuing to read. How does an element change its identity? Americium has 95 protons. After transmutation, it only has 93 protons and becomes the element neptunium. Neptunium has an atomic number of 93. Notice in the figure that mass and atomic numbers of neptunium and the alpha particle add up to the mass and atomic number of americium. No particles were destroyed during transmutation. Okay, so we have americium, 95 protons, 146 neutrons. You guys see how unbalanced that is? Yeah. Right? So it's like, well, no wonder it's going to be radioactive. Neptunium has 93 protons, 144 neutrons. and it ejects an alpha particle during the process. So if you add all those up, you get the same number. Number 5, calculate on the side. Did I miss number 4? I did. And 3. What happens to an element if it undergoes transmutation? It completely changes into another element. Very good. Number 4, define what are alpha particles made of. We just put in our notes. You've got 2 and 2. Very good. Number 5, calculate the element actinium has an atomic number of 89. How many alpha particles would americium need to lose before it became actinium? So we have 95 protons in americium, and we need to get down to 89. And we're counting by 2s, right? Because there's 2 protons per alpha particle. So what is 95 minus 89? 6. 6 divided by 2.
3.
So 3 alpha particles to go from americium down to actinium. Everybody understand how we got there?
Yeah.
How we did that? Fantastic. All right. What are beta particles? Yes. Oh, okay. So an alpha particle is a decay product that has 2 protons and 2 neutrons. Awesome, no problem. So what are beta particles? Not all transmutations cause the nucleus to eject an alpha particle. Some eject an electron instead. They call that special electron a beta particle. It is a high energy electron that comes from the nucleus, not from the electron cloud. Wait, what? Right? But the nucleus contains only protons and neutrons. So how could it give off an electron? In this type of transmutation, a neutron becomes unstable and it splits into an electron and a photon, or proton, excuse me. The electron or beta particle is ejected with a large amount of energy. I don't want to get into crazy detail, so it's one of those like just accept it for what it is. But there's definitely more if you wanted to investigate. You'd be getting into much higher level chemistry or physics. You'd be talking about things like quarks and neutrinos and things of that nature. Basically subatomic particles. And we don't need to get into that kind of detail for this class, but feel free. And if you want to nerd out sometime, I'd nerd out with you. What happens to the proton? After the electron is ejected, the proton stays in the nucleus. So that neutron turned into a proton and ejected the electron. It's a lot of ons. I know it's kind of hopefully not getting too confusing. Now there is an extra, one more proton in the nucleus, and the atomic number increases by 1. So it changes its identity, right? If you've got an extra proton, you are no longer what you used to be. The figure shows unstable hydrogen 3. 1 neutron splits into a proton and an electron. The electron, or beta particle, is ejected. Now the nucleus has 2 protons. Hydrogen 3 turns into helium 3. The mass of the atom stays almost the same because, as we said, the mass of an electron is very, very small. Off to the side, it says identify. Circle the beta particle in the diagram. So if we were to do that, you'd be circling this guy right here, right? That's your beta particle. Rate of decay. This is really, really important for our big picture question, right? So up on the board, I wrote big picture concept. How do we know the age of rocks, old bones, fossils, whatever? Okay, that's the big picture that we're doing in this Earth history unit. Okay, all of what we learn should in some way inform, you as far as how we can do that. All right, this is a big part of that right here. It says, have you ever watched popcorn pop? Have you?
Yeah.
How many of you have never seen like popcorn pop in a popper versus just in a microwave bag? Anybody have you never seen in the actual popper? No, just in a bag. Okay, it's fun to watch. You can get stovetop popcorn that actually like pops in a you can have a glass lid on it and do it that way with some butter. It's good that way too. Anyway, if you're not wanting butter, olive oil works really good. It's yummy. Anyway, you never know which kernel will pop next, it says. But if you have popped a lot of popcorn before, you might be able to predict how long it will take for half of the kernels to pop. Does that make sense, Stuart? If you've popped popcorn a lot, you might learn how to like predict how long it would take for half of the popcorn to pop. Okay. Radioactive decay is also is random. That's why radioactive decay is measured using its half-life. Half-life is a radioactive element half-life of a radioactive element is the amount of time it takes for half of a sample of the element to decay. I want you to put this in your notes, this definition. The half-life of a radioactive element is an amount of time. It takes half of a sample to decay into something else, right? The half-life of a radioactive element is the amount of time it takes for half of a sample to decay into what would be called its daughter isotope. So you start off with a parent isotope, you start off with some sort of element, and it decays into what's known as a daughter isotope. Turner, you good?
Yeah.
Okay. Oh, are we missing a pencil? Do we need a pencil? I appreciate you guys sharing and all, but we've got pencils. You're welcome. All right, how do we calculate it? The half-life of radioactive isotopes range from fractions of a second. So literally some parent isotopes will only last for fractions of a second for those really massive ones, often lab grown, okay? To billions of years. So some of them are radioactive, but just barely, essentially. They take so long to decay. Iodine-131 has a half-life of 8 days, pretty darn fast. If you start with 4 grams of iodine-131, after 8 days, you only have half that amount left. After 8 more days, you'd have only 1 gram, right? Another half. Okay. The radioactive decay of unstable atoms happens at a steady rate that nothing can change. So that radioactive decay, doesn't matter what the temperature is outside. It doesn't matter the pressure it's under. Okay, it's a constant. How are objects dated using half-life? We're going to go super in depth, but let's just read what they have to say here. Scientists use radioactive decay to find the age of fossils. Carbon-14 is a radioactive isotope of carbon. Its half-life is 5,730 years. It is used to find the age of dead animals, plants, and humans. Well, we're animals. Living things have carbon-14 in them because they take in and release carbon. When a living thing dies, the amount of carbon-14 inside it begins to decrease because of radioactive decay. Scientists can measure the amount of carbon-14 in an ancient item. Using the half-life of carbon-14, scientists can calculate when the animal, plant, or person lived. Let's look off to the side here, number 7. Calculate, if you start with 4 grams of iodine-131, how many grams would there be after 24 days? Show your work. All right, so we start off with 4 grams. And its half-life is how long? Its half-life is how long? 8 days. Only half-life of 8 days. And we're talking about 24 days later. Well, 24 divided by 8 days, what's 24 divided by 8? 3. Would we have any left? Well, let's see. After 8 days, you'd have 2 grams. After 16 days, that'd be cut in half again, so you'd be down to 1 gram. after another 8 days, which is our target, right? You'd have 1/2 of a gram, 0.5 grams left. Does that make sense? So you would have a little bit left, just not much. Do you ever get to 0, do you think? At some point you would, but it's going to take a while, right? Because you keep cutting everything in half. Technically, you'd never get to 0. In practice, at some point you're going to run out, right? Okay. How are objects dated using half-life? Scientists use, did I already read that? Yes, I did. Cool. Are we almost done? Ooh, we got plenty of time. That's good. Why are long half-lives sometimes a problem? Some radioactive isotopes have half-lives that are thousands, millions, or billions of years. Waste products that have these isotopes can be dangerous because they still release radiation. Sometimes we think of radiation in negative ways, right? Sometimes it's positive. Sunlight's radiation, isn't it? But some components of sunlight are more dangerous than others. Anyway, these waste products must be kept away from people and the environment. Special disposal sites are used to store this waste for long periods. Many of these sites are deep underground. So, for example, our nuclear reactors, the waste is radioactive. And you can't just put that stuff anywhere because it could hurt somebody or something or some animal. Making synthetic elements. There are only 92 elements found in nature. Other elements are made through transmutation. Scientists can smash alpha and beta particles into the nuclei of existing atoms to make new elements. Since these new elements are made by humans, they're called synthetic. Synthetic elements have greater numbers of protons and neutrons. They have atomic numbers greater than 92. What are synthetic elements? Huh? Yeah, elements made by people, artificial. What are the uses of radioactive isotopes? Scientists have made many useful isotopes. These isotopes, called tracer elements, can be placed in the body or released into the air. Then, scientists can use instruments to look for radiation while the tracer elements decay. Tracer elements have been used to diagnose diseases and study the environment. Tracer elements have short half-lives. With short half-lives are the best to use. The short half-lives do not expose living organisms to radiation for long periods of time. So, for example, iodine is sometimes put in like an IV drip or ingested perhaps, and they can watch it go through your digestive system or your urinary tract to see what's going on inside of you. Diagnosing diseases. Iodine is an element that is used by the thyroid gland. Radioactive iodine-131 can be given to a patient with a thyroid problem. The tracer element is absorbed by the thyroid gland. The radiation can create a picture of the thyroid, so it can be imaged. Doctors can then find out if the patient's thyroid is working properly. Study the environment. Tracer elements are used in the environment too. Scientists can inject them into the roots of plants to see how the roots absorb food. Others are put into pesticides. The tracer elements can then be followed to find out what happens to the pesticide in the environment. In other words, track it. Is it going to end up in our food, for example? Infer. Why might we want to know what happens to pesticides in the environment? Oh gosh, I kind of just gave that one away. Because pesticides might not be the best things for us to be ingesting. So seeing how long they last and stay in the food chain is, could be useful for us. Oh my goodness, we're done reading. Mini glossary. We've got atomic number. We already have that in your notes on your back of your periodic table. Beta particle. Did we take that down in our notes? I don't think we did. So beta particle, a high energy electron that comes from the nucleus, not the electron cloud. How does that happen? Well, because it used to be part of a neutron. So beta decay, probably want to put that in your notes. Beta decay is when a neutron is unstable and it turns into a proton and a little tiny piece of it gets kicked out as a beta particle. For the front of your periodic table, right next to where you have the alpha particle, go ahead and draw a small circle with a negative sign, and point to it and say, hey, that is a beta particle. It's an electron. It's also got isotopes defined for you there. I think we already had that in our notes too. Mass number, atomic mass, same thing, like an AKA, right? Radioactive decay, release of particles and energy from the nucleus, and transmutation, changing of one element into another through radioactive decay. Half-life you already took down, yes. Yes, so beta decay is when a neutron is unstable. It breaks down, it basically ejects an electron, and what's left behind is a proton. So a neutron changes into a proton and ejects an electron. And that electron that is ejected is a beta particle. Did I say that slow enough? And then you got a couple questions to answer, just two, although this one's got a couple boxes for you to fill in. Review the terms and their definitions in the mini glossary. Explain why the mass number, or atomic mass, and the atomic number of an element are different. Use complete sentences. That should be fairly easy. And then complete the table to explain what causes radioactive decay and what happens when particles are ejected. So here we have the two types of particles. The decay process for beta particle is actually given to you there. So beta decay, you're asking what to define it. It's actually right there for you, isn't it? This is the definition of beta decay. You will provide the description of alpha decay here. And here we have the result given to you for alpha, the alpha particle, and you need to put for the beta particle. Yes?
Down here, you said these two. Like, I can't pull them up on Google, right?
You
It
can't
says
pull
the
them
file
up.
can't be found.
Go to the next file up. It has all three chapters there.
Okay.
Yep. All right, any questions? Awesome. If I can hit stop.